Tools for Sequence Alignment. Presented for Bio4U.com. A lot of sequence alignment tools are available in bioinformatics. A few are FASTA, BLAST, Hammer, S-Suite, etc. This video explains a detailed account of the FASTA algorithm. The current FASTA package contains programs for protein, DNA, protein-translated DNA, with frameshifts, and ordered, or unordered peptide searches. Recent versions of the FASTA package include special translated search algorithms that correctly handle frameshift errors, which 6-frame translated searches do not handle very well when comparing nucleotide to protein sequence data. In addition to rapid heuristic search methods, the FASTA package provides search and implementation of the optimal Smith-Waterman algorithm. A major focus of the package is the calculation of accurate similarity statistics, so that biologists can judge whether an alignment is likely to have occurred by chance, or whether it can be used to infer homology. The FASTA package is available from the University of Virginia and the European Bioinformatics Institute. The FASTA file format used as input for this software is now largely used by other sequence database search tools, such as BLAST, and sequence alignment programs, Clustal, Keycopy, etc. Introduction. FASTA and BLAST are very popular tools for sequence alignment. In this video course, I am going to explain the FASTA tools and their implementation in brief. This course is specially designed for bioinformatics students of an undergraduate and postgraduate student, and anyone who is interested in bioinformatics and sequence. In this course, I am going to cover 1. FASTA 2. FASTA algorithm 3. FASTA implementation 4. FASTA output as result. FASTA algorithm. The FASTA algorithm is a heuristic method for string comparison. It was developed by Lipman and Pearson in 1985, and further improved in 1988. FASTA compares a query string amongst a single text string. When searching the whole database for matches to a given query, we compare the query, using the FASTA algorithm, to every string in the database. When looking for an alignment, we might expect to find a few segments in which there will be absolute identity between the two compared strings. The algorithm is using this property and focuses on these identical regions. It is a word-based method. It looks for matching word, or the sequence patterns, called k-tuples. It then builds local alignment based on the matches. Process of FASTA algorithm. There are 4 steps in the FASTA algorithm process. The first step is find runs of identical words. This will identify regions shared by the two sequences that have the highest identity of single residue identities, DUP equals 1, or 2 consecutive identities, DUP equals 2. Observe the diagram, which gives the result of the first stem. The words of 2 sequences are aligned as single residues. Second step is rescore using PAM matrix. It keeps the best score. It rescan the best regions identified in step 1 using the percentage accepted mutation, or PAM 250 matrix. The single best score is stored as init 1 for reporting later. Observe the diagram, which shows the best score aligned. Step 3. Join segments, using gaps, and eliminate other segments. It determines if gaps can be used to join the regions identified in Step 2. If so, determine a similar score for the gapped alignment, which is reported as int. See the figure, the gap is shown. Step 4. Use dynamic programming or DP to create the optimal alignment. Construct an optimal alignment of the query sequence and the library sequence, Smith-Waterman algorithm. This score is reported as the optimized score. Here, the width of the 2 bands is the parameter.
First of all, you just type in the address bar, that is the ebiki.uk/tools/FASTA and /. Then you will get a new window, and this window will appear like this. So it is actually the FASTA window, And in this FASTA window, there are a lot of options are there. That is a protein, a sequence analysis, nucleotide, genome, proteins, etc. So we are interested in the protein. So just click on the protein, and then you will see that protein similarity search. So in this protein similarity search, you can see step number 1 and select your database. So a lot of database, different type of databases are available here. So as per my view, it is better to initiate for the beginners UniProt and SysProt database. So select this one. Then you can see that this step number 2. Then in the step number 2, they are asking to enter your input sequence. The input sequence is better in the FASTA format. So FASTA format means starting with greater than sign. So for that, I am not going to input a new data. I will take an example for just to clear the how the procedure will go forward. Okay, so I will take an example. Here is the example sequence. Click here. So an example sequence is appeared here. This example is actually begins with a greater sign. So that greater sign indicating that the sequence is in FASTA format. Okay, so this is actually human insulin like growth factor binding protein complex. Okay, so this is the FASTA sequence we input as an example. Okay, otherwise you can select your file, or you can input in the FASTA format any protein sequence or DNA. So if you select here protein, you should input the protein sequence, or if you DNA, you must input the nucleotide sequence. Okay, so then go to the step number 3, set your parameters. So the parameter we are going to study the FASTA similarity search. So FASTA is the target. Okay, and more options you leave this at this moment. And then step 4 is the submit your job. Okay, so if you want email, then you click here and give the email. So otherwise you leave it free. Okay, so I think it is better to give email because it will take a long time for the submission. After the submission, the result will appear. It will take a little time. So if the sequence is longer, it will take a long time. So if the sequence is short, as the sequence is see here, the sequence is very short, it will not take that much time. So I will go without giving the email ID. Okay, I got the result here. So in the result section, you will see summary table, tool output, visual output, functional prediction, submission details. Okay, so in the summary table, you can see the different similarity search. The similarity search that is showing 100%, it is a well and good. So you can select this one. Otherwise, if not 100, the nearest, the highest value, those having the highest value that you select, and you proceed the further study on this sequence. Okay, then another one I will show the different options here. Then tool output, click on the tool output. It will lead a new window. In this window, you can see the different tool output. So here all human insulin like growth factors. So there are a lot of sequences are given here. And here, see here, this is the 0, and 0 means the maximum alignment is on the 0. Otherwise, 1.5 E means actually the negative value. It is very near to 0, but 0 is better than near to 0. So this is the best candidate. You have to select this one and proceed the research forward. Okay, so here download, there are so many download options, download XML format, etc. Okay, then let us see the visual output. So in the colored visual output, it will give. So see how it appearing. Okay, this is the colored output. So here the beautiful colored output is given, and you can select any one, and you can use this chart as such in the research paper, or you can study further and interpret your result as per the visual output. Okay, or you can download in SVG format also. Click here to download SVG format. Here two option given, one fixed and then dynamic. Dynamic is better because dynamic will show the changes at the fraction of second. If you fix it, it will fix, no change will take place. Okay, then next functional prediction. when you click on the functional prediction, it will lead to a new window. In this window you can see the different functional, the sequence will split and it will show the different sequences, and whatever you want, you click there and select as per your need. Okay, so this is the visual functional predictions, and finally you can see here the submission details. So in the submission details, all the details that you used to submit the sequence that will appear here. For example, sequence, it is a protein, matrix BL50, match, mismatch, scores none, open -10, and the most important is the K-tup. It is a tup. Mostly the proteins, we take a protein, so it is in between the 1 and 2. If it is a DNA, it is near about 5 to 20. Okay, so that is the output of the FASTA program, or the FASTA parameters. Okay, so you can use this data for your research purpose also. Okay.